Last class we talked about more stuff with rotational motion, that being rotational kinetic energy and conservation of angular momentum, and just how that plays into the idea of torques as well, with regard to the sum of the torques is equal to I, the moment of inertia, times the angular acceleration that some object is experiencing. And so it's important to be able to analyze certain situations both from looking at torques and also looking at conservation of energy, because both are important. So if we have, say, a pulley, and we have two blocks on our pulley. Say we have M2 and M1, okay? And we have our pulley, which, let's say, is a hollow cylinder, which is allowed to turn on some central axis right here. So it's positioned on some rod that therefore will let it turn. This has a different moment of inertia than a solid disc would. So this moment of inertia is equal to its mass times its radius squared. And so first of all, let's look at the kinetic energy, well, just the energy situation in general here, that if we say there's no friction involved, and we have mass 2 here being heavier than mass 1, well, being larger than mass 1, and set the system in motion, mass 2 will fall, mass 1 will go up, and the pulley will turn clockwise. Okay? So we can look at what happens if we let this go, and say in a couple seconds later what happens, or as this has fallen a certain distance what happens. And if there's no friction, remember that we have WNC is equal to, so any non-conservative work, is the change in kinetic energy for movement, translational movement, plus any rotational motion, plus some change in potential energy. There's no spring involved here, and so that means that this is going to end up being just the potential due to gravity. I could have put a spring down here and said what happens afterwards, but let's keep it a little simpler first. So we have to look at the change in this translationally, rotationally, and gravitationally. And if there is no non-conservative force involved, this side is 0, so that means that the energy before equals the energy after, because 0 is equal to the change in all the energies together. So we would have KETI plus KERI plus PEI is equal to KETF plus KERF plus PEF. So in this situation, what can have translational kinetic energy? That would be the two blocks, because they are moving in space. What can have rotational kinetic energy? That would just be the pulley, because that's the only thing that's turning. Okay, so, and then what has gravitational potential energy that's changed, that would be both these two blocks. So you would plug that in there, and then rearrange to see what happened. So you could say that this one was at a certain height, that was at an initial position of h, and it goes to a final position of 0, and this one will have some other delta h that will be the exact opposite of that. So if this goes down 5 meters, that goes up 5 meters. So right now I'm just going to label that as PE1 initial and PE2 initial. And KET initial for both of them is going to be 0. And for the block, for the pulley itself is going to be 0 if it's not spinning. So we can simplify our equation this way. So we have the potential energy of these two blocks is equal to the potential energy of them afterwards, plus the kinetic energy of the two things, that being the translational energy and the rotational energy. So the translational of these two and the rotational of that one right there. Okay. So what does that look like? That says that PE initial is equal to 1/2 M1 V final squared plus 1/2 M2 V final squared. Why did I not write final on there? Because they're going to be moving at the same velocity since they are connected by a string. And then we have the addition of 1/2 I omega squared for the pulley and its angular velocity. That's what's involved there for the rotational kinetic energy. And then the PE final. So I'm just going to keep the PEI and PE final in general and look at this, because what's important here to note is that the angular velocity of this pulley is related to the velocities of these two objects. How? Well, the tangential velocity of the pulley is the velocity that is moving at some point on the edge, and Vt for that is equal to its radius times the angular velocity. And so, that means we can plug omega equals V over R into right there for omega. So now we have everything in terms of V, the linear velocity of these two objects, and the tangential velocity of this pulley, and that makes everything simpler. And then therefore you can plug in mr squared for the I right there. The r's end up canceling, which is nice, and you end up being able to redefine your situation in terms of that velocity so you don't have so many equations. So you can just solve this and you'd be done. If instead you were looking at this from the torque aspect, then what would you do? You'd have to say the sum of our forces is equal to mass times acceleration, and the sum of our torques is equal to I times an angular acceleration. Okay, so you have to look at both of these two things and see what's happening in here, and be able to write equations and then solve. So we would have to look at, say, for M1, what's going on. For M1, we have the force of gravity going down, and we have the tension going up. And so the sum of our forces would then be plus T1 minus M1G is equal to positive M1A. Why positive? Because it's going up. So I'm putting in the direction for A right there. For M2, we have a similar free body diagram where we have Fg going down and we have T2 going up. So we would have plus T2 minus M2G is now equal to minus M2A since it is going down. And the accelerations are equal because they're connected. Okay. And T2 and T1 are not equal because this pulley has to move. If T1 and T2 were equal, then the pulley would not be moving, which is evidenced by this free body diagram for the pulley, where we have T1 pulling on this side and T2 pulling on this side. So if we look at the torques involved in this, we know that if T2 and T1 are equal, the pulley is not going to move. If one of them is bigger than the other, however, it will actually change. And so, using this, the sum of our torques is equal to the torque from T1 and the torque from T2, and the torque from T1 is going to make it go counterclockwise, so that would be positive, and the torque from T2 is going to make it go clockwise, that would be negative. So the sum of our torques is equal to minus the torque from, well, plus the torque from T1 minus the torque from T2, and that's going to equal our moment of inertia times the angular acceleration of this pulley. Now, what direction is the pulley going? It's going clockwise, and therefore alpha is going to be negative. So if I put in the actual negative sign, then I can take off the vector nature of the alpha. So I have torque of T1 minus torque of T2 equals minus I alpha. What is the torque of T1? That would be the value of T1 times the distance it is being applied from the axis of rotation times the sine of the angle between them. So that would be a 90-degree angle, because it's being applied tangentially to the circle. So we have T1 times the radius of our circle, or radius of our pulley, minus T2 times the radius of our pulley is equal to minus I alpha. And just like we could relate V and omega in the energy case, we can relate A and alpha in this case. So because the rope is going over the pulley, because the rope is moving the pulley, causing the pulley to turn, then its acceleration, its angular acceleration is related to its linear acceleration, the tangential acceleration, by, let me write that over here, A is equal to R alpha, just like V is equal to R omega. And so that means that this is equal to minus I times A over R. And then you can take this equation, and this equation, and this equation, and set things equal to each other, and solve for acceleration, and then solve for whatever else you need to solve from there. So you can attack this problem either from the conservation of energy approach, or from looking at the torques and the forces that are involved. And since the energy approach does not involve vectors, it usually is the easier one to go with than looking at the conservation, than looking at some of the torques and some of the forces. But both give you the same result, as it should, since both are describing the same phenomenon, the same situation of the rotational motion, coupled with the translational motion, coupled with a change in height.